Now let's talk about buoyant force and Archimedes' principle. Buoyant force is the upward force exerted by the liquid on an object immersed in or floating in the liquid itself. Buoyant forces are the forces that keep objects afloat. So in this case, if the weight of the cargo ship is acting downwards, the fluid is acting upwards, and so that it floats at its surface. It's almost, not quite, but it's almost the same as saying the normal force in case of the two solid surfaces in contact always have a normal force that acts perpendicular to them. The same way, buoyant force always acts perpendicular to the surface. So when we talk about floating objects, the lighter object will obviously will require less buoyant force, and so it will be floating higher, whereas a heavier object, since it requires more buoyant force in order to keep it floating, it will be immersed more into the liquid that it is lying in. Same thing between oil tankers. For an empty tanker, the water line will be probably a lot higher than for a full tanker filled with a lot of mass, because it's the buoyant force basically that's keeping it afloat. Another very interesting phenomenon is floating in a cup of water. So the idea is that in order for something to float, you don't need a lot of fluid underneath, but you basically need some fluid so that the fluid can apply a buoyant force to keep it up. Another important factor is Archimedes' principle. Archimedes' principle describes the magnitude of a buoyant force. The buoyant force exerted by a fluid on an object is equal in magnitude to the weight of the fluid displaced by the object. Any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to its weight, to the weight of the water or fluid displaced by that object. So let's look at it in a little bit more detail. So if I was to draw a free body diagram of an object floating submerged into a liquid, this is what it would look like. So it will have a weight that acts downwards, it would have a buoyant force that acts upwards, and probably another force that's acting downward would probably be due to the atmosphere. So the total force on the block due to the fluid is called the buoyant force. A buoyant force will be equal to F2 minus F1, where F2 has to be greater than F1 in order for anything to keep afloat. So the magnitude of the buoyant force will be given by this expression here, F2 minus F1. F2 is P2A minus P1A. Delta P1A will be given as F of B will be given as rho G D A, where P2 minus P1 will be equals to rho GH from before, from the last section that we were talking about, where A and D together will make up the volume. So the buoyant force will actually be given by rho G and the volume of the material that is displaced. Now this is very important to remember. It is the volume of the fluid that is being displaced. Right? So in a nutshell, Archimedes' principle states a fluid exerts an upward buoyant force on a submerged object that is equal in magnitude to the weight of the volume of the fluid displaced by that object. And mathematically it will be given by rho G V. So now let's look at an example. A flat-bottomed barrage loaded with coal has a mass of 3 times 10 to the 5 kilograms. The barrage is 20 meters long and 10 meters wide. It floats in fresh water. What is the depth of the barrage below the water line? In order to do this, let's draw the picture. So here's my barrage, and here's where my water level is. Okay. Now, what do I know? I know that there is going to be a weight that is acting downwards, and there is going to be a buoyant force that is acting upwards. Now, the question gives me that the mass of this barrage is 3.0 times 10 to the 5 kilograms. It also gives me its length, which is 20 meters, and it gives me its width, which is 10 meters. So basically, if I have both of these, I can calculate area, which is length times width, which comes out to be 200 meters squared. right? And then it says that it floats in fresh water. So that also gives me another information that rho for fresh water is 1,000 kilograms per meter cubed. Okay. And what is it? What is the question asking me? The depth of the barrage below the water line. So this is the little tiny depth that I'm looking for. I'm going to call this D. So D is what I want. Okay. So if I was to write my force equations, it would be sigma Fy, in this case, will be F buoyant minus mg. Okay? Since this barrage is not accelerating in the y direction, even if it is accelerating in the x direction, it's not accelerating in the y direction, so sigma Fy will always be equals to 0. So this implies F buoyant is going to be equals to mg. So remember how we did that other calculation before where we called m equals rho v, where rho is the density and v is the volume? So all I have to do now is calculate plug this value in here to get rho vg. Also, I know for the buoyant force, this is going to be the rho of water plus the water displaced times g. Actually, I may not need to convert this because it's already giving me the mass of the barrage. So I may not even have to know this because this is being given to me. So all I need is mg. Okay, interesting. Now, rho of water I know is 1,000 kilograms per meter cubed. V is the volume of the water that is displaced. So this is going to be the area times d. This is what the water displaced is going to be. G equals mg. G goes away. Mass is given. Area I just calculated. So this is going to be 1,000 times the area, which is 200, times d is the mass that's given, 10 to the power 5 kilograms. So all I have to do now is rearrange a few things and calculate what the depth is going to be. And for me, I calculate it to be about 1.5 meters. It's just a matter of plugging it into a calculator and solving for it. So a barrage that is 20 meters wide and 10 meters in width and length of 20 meters that carries a mass of about 3 times 10 to the 5 kilograms will have to be this much below the water surface. Another example, a piece of metal is released underwater. The volume of the metal is 50 centimeters cubed. So 50 centimeters cubed, note what we have to do here. And its specific gravity is 5. What is its initial acceleration? So note when v equals 0, there should be no drag force. So now in this case, it says a piece of metal is released underwater. So here's my water, and so let's say whatever shape that material is, it's irrelevant right now. The volume of the metal that it's giving me is 50 centimeters cubed. So the volume of this metal that is being released is 50 centimeter cubed. Now in order to convert it right away, you know 100 centimeters is equals to 1 meter. But since this is cubed, I have to cube this one too. So that is going to be the volume of the metal. Let me just write M for metal. Okay, and it says at specific gravity is 5. Now specific gravity is a very interesting thing. Specific gravity is the density of, for example, that metal divided by the density of, this is by definition, the density of water that it is immersed in. So just remember that, then the value of this is going to be, it's given to be 5. Okay, and what is its initial acceleration? So the question asks me, what is the initial acceleration? Given that its v naught, or initial velocity, is 0 meters per second. And in order to do that, I'm going to find all the forces that are acting on this metal. Well, one is going to be the mg, which acts downward. Excuse me. And then there's going to be a buoyant force that's going to be propelling it upwards. So if I was to write the force equations, sigma Fy will be equals to Fb minus mg. Now in this case, since the motion is going to be upwards, my will be may. Okay? So that means it's going to be may equals the buoyant force minus mg. And this is m of the metal, whatever m of the material that it is being used in is. And this is also m of the metal. So if I was to solve this, and I need ay only, so ay will be buoyant force divided by mass of the metal minus g. Now the question is, what is buoyant force? Now here's what I think we need to do in order to solve this. So buoyant force, as I know from before, is equals to rho of water, right? V, that is displaced, volume of the water displaced, and G. So I need to be able to plug that back into here. Now what do I get? I get rho of water, V displaced, and G divided by M. Now here it doesn't give me an M, but it does give me the volume. So I can convert M equals, so I know rho equals mass over volume. So mass is going to be density times the volume. So the density of the metal times the volume of the metal instead of M minus G. Now look very carefully. I defined my specific gravity to be rho of the metal divided by the rho of water. So do you see that somewhere here? Yes, right here. But the specific gravity is going to come towards the bottom, and that's okay. So the volume that is displaced times G times specific gravity and volume of the metal, which is given, minus G, will give me my initial acceleration. Now, how do I find the volume displaced and the volume in the metal? If this is the volume, is the volume that this whole thing displaces the same as this volume that moves up? And the answer is yes. For the submerged objects, once they are submerged, V displaced is the same as V of the entire metal. In that case, these go away, and we are left with 1 over specific gravity minus 1 times the acceleration due to gravity. Okay? And the specific gravity is given to be 5, so I literally have to plug in 1 over 5 minus 1 times G. Okay? Which, when I solve it, I'm going to rewrite it over here, I get acceleration to be equals to minus 7.8 meters per second squared. Okay? And that is going to be what my initial acceleration is going to be.